I welcome back all to the course on control system engineering. In this video, we are going to learn the mathematical modeling of AC servo motor and synchros. Before start the present discussion, let me recall what we have learned in the previous video. In the previous video, we learned the mathematical modeling of DC servo motor to control the speed of the motor using armature control and field control. In armature control motor, the field voltage kept constant and the speed and torque of the motor is directly proportional to the armature voltage. Whereas in the field control motor, the speed and torque of the motor is directly proportional to the field flux due to the armature voltage kept constant. Now we'll go to the mathematical modeling of AC servo motor. The AC servo motor is a two-phase induction motor. In the normal induction motor, the rotor resistance is very large, thereby X by ratio is very small. Therefore, the torque speed characteristics are nonlinear. Whereas in AC servo motor, due to its two-phase windings, the rotor resistance is very large. Therefore, X by ratio is very small that causes linear torque speed characteristics. Therefore, the control of the speed is very smooth in AC servo motor. Due to the two-phase induction motor, the AC servo motor is having two windings. One is reference winding, second one is control winding. And these two windings are placed at right angles, that is 90 degrees apart. And the reference voltage is supplied with a fixed AC supply voltage, and the control winding voltage is also the same frequency, but the phase difference is 90 degrees. These two windings causes a magnetic flux induced in the stator of the motor that causes the rotor to rotate. This angular displacement of the motor is fed back to the AC amplifier through the potentiometer. Since the reference position is already defined, the error signal will be amplified and given to the control winding. Because of the positive, when the error signal is positive, this rotor will keep on rotate and reaches its desired position. When the error signal is negative, it rotates in opposite direction. So this control takes place until the error signal is equal to 0. This is the basic principle of AC servo motor. Now let us see the transfer function derivation of AC servo motor. Here the torque developed by the motor is directly proportional to the control voltage as we have seen in the previous slide. And also the torque on motor is directly proportional to the angular velocity. Therefore, the torque developed by the motor is equal to K1 into EC minus K2 into d theta by dt, where minus indicates as the angular velocity increases, the torque decreases. Say this is equation number 1, and then the torque applied on the load, that is load torque, is equal to J into d square theta by dt square plus B into d theta by dt, and say this is equation number 2. Therefore, at the equilibrium, these two torques must be equal. Therefore, from equation 1 and equation 2, we have J theta d square theta by dt square plus B d theta by dt is equal to K1 EC minus K2 d theta by dt. By taking the Laplace transform on both sides of the equation, we have Js square theta of s plus Bs theta of s is equal to K1 Ec of s minus K2 s theta of s. After taking common theta of s from all the terms, we have Js square plus Bs plus K2s into theta of s is equal to K1 Ec of s Now, if we take the ratio of theta of s to EC of s, we will have k1 by s into js plus b plus k2 after taking common s. If that is equal to, if you take common b plus k2 constant term from the denominator and then to numerator, we'll have k1 by b plus k2 by s into j by b plus k2 into s plus 1, that is equal to km by s into tau m s plus 1, where tau m is the mechanical time constant. This is our desired transfer function of the AC servo motor. Synchros are the electromechanical devices which produces the voltage depending on the angular position of the rotor but not on the speed. The synchros are also called Celsin, Telesin, and Anderson. See, this is the example of synchros. Here, when you produce, when you rotate the shaft of the transmitter by an angle of theta, the rotor will rotate by the angle theta degrees. Then the synchro transmitter will convert this rotation by the equivalent voltage. The voltage will be transmitted from the transmitter to the receiver, where the transmitter connected at a distance. At the receiver side, the synchro receiver will convert again the voltage to the mechanical rotation. Therefore, the rotor at the transmitter side will be rotated by the angle theta degrees, which is exactly equal to the rotation taken place at the transmitter side. So thereby, the mechanical rotation will be transferred from the transmitter to the receiver using synchros. This is the concept of synchros. Now let us see the synchro transmitter construction and its working principle. In the construction features, you can see the major parts of the synchro transmitter are stator and rotor. The stator of the synchro transmitter is of three-phase induction motor. Therefore, we have three stator windings, S1, S2, S3, and these three stator windings are placed 120 degrees apart. And the rotor construction is of dumbbell shape and it has only one single winding. The two ends of the rotor windings are terminated on two slip rings, and the single phase AC excitation is applied to the rotor. When the rotor is excited by the AC voltage, the rotor current flows and a magnetic field is induced. The rotor magnetic field induces an EMF in stator coils by the transformer action. So here the rotor is acting as a primary winding and stator is acting as the secondary winding. Therefore, when the excitation is applied to the rotor, that causes an EMF at the stator winding. It's the ac- depending on the alignment of the stator coil axis with respect to the rotor coil position. Let us assume the instantaneous value of the AC excitation given to the rotor winding is ER sine omega t. Then, by the transformer principle, when the voltage transfer from the primary winding to the secondary winding, the EMF induced in the secondary winding is multiplied with the number of turns and the coupling coefficient. Therefore, the EMF induced in the stator coil is equal to KT into Kc into ER sin omega t, where Kt is the turns, number of turns in the secondary winding, that is the stator windings here, and Kc is the Kc is the coupling coefficient. Let us assume The secondary winding S2 is the reference vector. Then the flux induced in the secondary winding S2 or the stator winding S2 when theta is equal to 0 is maximum, and the flux induced in the stator winding S2 is 0 when theta is equal to 90 degrees. And since the coupling coefficient Kc for coil S2 is equal to K1 cos theta, and the coupling coefficient Kc for coil S3 is K1 cos theta minus 120 degrees, because of the two secondary windings or the stator windings are placed 120 degrees apart. Similarly, the coupling coefficient Kc for coil S1 is equal to K1 cos theta minus 240 degrees. This is when the rotor is rotating in anti-clockwise direction. Therefore, the EMF of stator coils with respect to neutral terminal, since it is connected, all the stator windings are connected in star connection, the EMF induced in the secondary stator winding S2 is equal to K2 K1 cos theta. This is the coupling coefficient K1 cos theta, and ER sin omega t, that is equal to K ER cos theta sin omega t, where K is the constant which is equal to KT into K1. Similarly, the EMF induced in the stator winding S3 is equal to KT K1 cos theta minus 120 degrees ER sin omega t, that is equal to K into ER cos of theta minus 120 degrees into sin omega t. Similar way, ES1 is equal to KT K1 cos of theta minus 240 degrees into ER sin omega t, that is equal to K into ER cos of theta minus 240 degrees into sin omega t. If you take the differential EMF, that means coil to coil EMF, we have ES1 S2 is equal to ES1 minus ES2. That is equal to, if you solve the above two equations, ES1 equation and ES2 equation, we will get root 3 into K ER sine of theta plus 240 degrees into sine omega t. Similarly, ES2 S3 is equal to ES2 minus ES3, that is equal to root 3 into K ER sine of theta plus 120 degrees into sine omega t. Similar way, ES3 S1 is equal to ES3 minus ES1, that is equal to root 3 into K into ER sine theta into sine omega t. Therefore, the mechanical rotation of the rotor is converted into the electrical voltages at the stator windings. This stator winding induced EMF are transmitted to the synchro receiver or synchro control transformer to convert these voltages back to the mechanical rotation to drive the load connected to the motor. The constructional features of synchro control transformer are very similar to the synchro transmitter, but the difference is rotor shape. The shape of the rotor is here cylindrical shape, so that the air gap is practically uniform. And the working principle of synchro control transformer is when the EMFs induced in the stator windings are applied to the control transformer, then these EMFs are converted into the mechanical rotation depending on the rotor position and the EMFs applied to the stator windings. Thereby, this rotor position controls the load connected to the motor winding. The synchro error detector is formed by the interconnection of synchro transmitter and synchro receiver or control transformer. The stator in this synchro error detector, the stator winding of the synchro transmitter are directly connected to the stator windings at the control transformer. When the AC voltage is applied to the rotor winding of the synchro transmitter and the rotor is rotated by an angle of theta, then there is an EMF induced in the stator windings of the synchro transmitter. Since these stator windings are directly connected to the transformer, control transformer stator windings, there is an EMF induced in the stator windings of the control transformer that causes a rotation at the rotor through slip rings, and it causes the rotation of an alpha, thereby with respect to the null position. Therefore the net angular displacement in the two rotor windings are is theta 90 degrees minus theta plus alpha. Therefore the voltage across slip rings of control transformer is given by Em is equal to K dash into Er cos of 90 degrees minus theta plus alpha into sin omega t. If we take minus common from the angle, we get Em is equal to K dash Er cos of 90 minus of theta minus alpha into sin omega t. Therefore, Em is equal to K dash Er sin of theta minus alpha, because cos 90 degrees minus theta is equal to sin theta. Therefore, cos becomes sin of theta minus alpha into sin omega t. Since if you assume theta minus alpha is equal to phi of t, then Em is equal to K dash Er sin phi of t sin omega t. When the theta minus alpha, the angular displacement between two rotor windings is a minor or small value, then it is approximately equal to 0, then sin phi of theta t is equal to approximately equal to phi of t. Therefore Em is equal to K dash Er phi of t sin omega t, where K dash is the proportional constant and phi of t is equal to theta minus alpha. This is the modulated error signal of synchro error detector, which is proportional to phi of t and also depends on sin of the phi of t. This modulated error signal is demodulated by the signal conditioning circuit to drive the motor. Since the modulated signal is proportional to phi of t, the demodulated signal is also proportional to phi of t, and it is the proportionality constant is the sensitivity of synchro error detector. Therefore, E is equal to Ks into phi of t. After taking Laplace transform, we have E of s is equal to Ks into phi of s. Therefore, the transfer function is given by E of s by phi of s is equal to K of s. In this video, we have learned the working principle of AC servo motor and the transfer function derivation of AC servo motor. And also, we have learned the working principle of synchro transmitter and control transformer. And also, we have seen an application of synchro as an error detector by deriving its transfer function. In the next video, we'll learn about electrical first order and second order systems and their responses for different input conditions. Thank you.